Okay, so this is going to conclude really the internal flow stuff, because what we developed were ways to calculate these friction factors, right? Which tell you about losses in pipes, and then we apply those to getting from fluid from point A, any wild way of pipes that we have, all the way to point B, right? So we did some analysis, we figured out laminar things, we figured out turbulent friction factors, right? We're trying to figure out what pump do I need to get my fluid from A to B, given given energy requirements, and we developed that, and this is this whole concept then of major losses and then minor losses, which account for viscous losses based on your fluid or viscous losses based to them being in pipe. So these are pretty important, right? How to get those friction factors. And to get them, you could use a Moody chart, or you could use the equations that you have and have computers do them for you. So for any sort of multi-pipe system, if it's like in the notes I drew this picture, it's just really helpful to just go right back to circuits where this is some flow resistance, right? Same thing. It's not exactly like but it sets you up in a place where you could at least know what type of equations you have to write down. Okay? If I get, and there's so there's here there's H1, H2. So there's a great potential difference across the circuits, and we say K2 and then K3, where this is flow resistance values. It's right, any sort of piping system you can rationalize in some sort of electrical circuit, you're going to be way closer to getting the correct values, or understanding how to get them, right? Because in this section rules, and now in this section rules, there's some now head loss across here, right? And this, right, the idea is from here to here, the head loss from here to here, in reality is that Bernoulli's, right, is this Bernoulli statement, where you have the difference of velocities and things like that. But right, when you're just trying to figure out viscous head losses, you have to sum up. This is the way I like to think of it. Fi, length I, squared, and we have to the fifth G, and that would be in this section. And remember that when it comes to these resistor values, I write it this way because when it comes to the minors, I found effective lengths and plugged them into this. So I just kind of have one equation to deal with. So that would give you the head loss from here to here. Let's say H2, this H3. Right. You also know the head loss here, kind of. So this, and then you would write out the head loss here. You would do the same thing. This would be 1, 2, 2. You could also write out 2 to 3. It's just one of them. This is an example too, right? 2, this has to be the same. And then you have this parallel unit, right? Something you know about this section as the things before, where I know that all of these have to be the same head losses. So if this is like A, B, C, you know that all of them have to be the same. Okay. And what else can we write down? Well, you also know that you would also know that Q12 has to equal QA plus QB plus QC. And I just want you to get a sense of now, if you write these like circuits and you have those laws of the flow rates like that, whatever types of things you're trying to find, you have these methods to write down these equations to get the values that you want. And this is a hard problem actually because of this nonlinearity that happens from going from this series pipe problem to a parallel pipe problem to another series pipe problem. Right? But you can do it if you just write down all these equations that you know must be true. I know that the flow rate in this section has to equal the flow rate amongst all these. Now you go to here and can calculate, you understand, coupled with this problem right here, and you know all these resistances in there, or you don't know them, you're going to be able to calculate a head loss over here. If you get one of them, well, now you have the total head loss, etc. There's an infinite number of problems that you can get for piping problems. What's more important is you know which one of these matter the most. You have the head loss equations for multi-pipe flows, and then you also have these flow rate conditions for parallel, and then for series, you know that all of these flow rates have to be the same. Those are the important things you have to remember. And figuring out what givens and what unknowns you need to get from that, well, that's on you. And I think that's a critical skill to know. But sometimes I think it's important to understand what's available to you to write down. And that's the head loss equation and these flow rate equations. So with that being said, your project is just a bunch of pipes in series, and then there's one parallel question I put in the water distribution, right? And I would say there's an example in the book that goes over this parallel distribution problem, but that is a good challenge that I would put on you guys for that last problem. Everything else is just a bunch of pipes in series and looking for viscous losses. But other than that, there's going to be that parallel problem of the water distribution in OHSU, and that's it for these pipe problems, I believe. So next is going to be external flows, which are involved with a lot of cool things, and I like external more than internal just because there's a cool math that happens in it. But you'll see the same type of process go down where we are going to look at external flows in a very simple case and develop these drag coefficients or friction factors, and then we're going to develop ways to calculate energy. So if it's an applied class, it means you're calculating energies. Always.